Hello, everyone. Welcome to today's webcast on Design for Additive Manufacturing Principles. I'm the moderator, Krista Prokos. Before we get started, I want to let you know that you can submit questions for today's presenter by typing them into the Q&A panel at any time. We'll collect them and address them at the end of the presentation. Now, I'd like to introduce our presenter. We're happy to have with us today Simon Indrele. Simon is an application engineer at Fisher Unitech and an additive manufacturing expert. Simon, take it away.
Thank you so much, Krista, and thank you all for taking this time out of your busy day to be here with us. My hope here today is to have you leave with some new information, something for you to be able to think about long-term regarding how your organization approaches additive manufacturing and what avenues can be taken to improve it. So before we dive into the presentation, let me tell you a little bit about myself. My name is Simon Indrele. I'm a 3D printing application engineer here at Fisher Unitech. I'm a Stratasys certified application engineer and have been in the 3D printing industry for 13 years now. Most of those have been split between production and application engineering. Some of my other areas of expertise are 3D scanning and reverse engineering, which tie really well into 3D printing. So now that we got that out of the way, let's talk some 3D printing. One thing I'd like to preface is that there are a multitude of different 3D printing technologies. As you may know, 3D printing started in the 80s, and since then, quite a few different technologies have been developed. The ones you see here on the screen are just the ones I can come up with off the top of my head, and there, I'm sure, are many more that I forgot. DFAM, or Design for Additive Manufacturing, will be applied differently to different printing technologies. Optimizing a part for one particular technology could affect it negatively if printed on another technology. So I really just want to highlight the fact that different technologies require different optimization techniques. So keep that in mind throughout this presentation and in the future when you're out in the field. You may have noticed that the FDM and PolyJet technologies are marked in bold, and that's because those are the two technologies that we will touch on in this presentation. Before we jump into DFAM, I want to spend a few slides showing you some of the cool new things that are available for both FDM and PolyJet technologies. Some things that hopefully we weren't aware of and perhaps could spark some new ideas for you. Stratasys is a wonderful portfolio of FDM printers ranging from the tiny capable Mojo all the way to the F900, capable of printing 3 feet by 2 feet by 3 feet. So there's really something for everyone as far as material capabilities, build envelopes, and so on. One particular printer I'd like to touch on is the F1G3 series. It's a well-rounded machine, significantly improved throughput over the previous generation, has super simple to use GrabCAD print software, which allows native CAD file import, so no more mess around with STL files. And there are many, many more benefits that we don't have time to list here today. Some of the new materials that are available, one of them is nylon 12 carbon fiber. It's the highest strength and stiffness to weight ratio material Stratasys offers. It rivals aluminum as far as mechanical properties, so we're seeing a ton of applications that are using it to replace metal parts. Really exciting stuff. The newest material out there right now is called Antero 800NA. It is a PEX-based material, so that's polyether ketone ketone for any of the chemistry folks out there. The three main takeaways here are very high chemical resistance, high temperature resistance, and ultra low outgassing. So if you have any applications requiring those kinds of properties, this may be the material for you. Really great for any clean room applications due to its mentioned low outgassing. And just a quick few highlights about PolyJet technology, and we'll get right into DFAM. So one of the newest materials for PolyJet line is called Agilis 30. It's meant to simulate rubber material. So by its name and its basic form, it's a short A30 material. But due to the fact that it's PolyJet technology based, rigid materials can be added to it during printing to create a range of materials from short A30 to short 95. And also, now vivid materials have been added to the J750, the flagship PolyJet machine, which adds its color capabilities now to over 500,000. All right, and now let's jump into Design for Additive Manufacturing. So, additive has the potential to be a revolutionary addition to your traditional manufacturing capabilities, but there's a reason I said potential. The reason is because it can be implemented in two distinct ways, either very poorly or very well. Which path you choose will determine just how great of a tool it can be for you. So as you can see here on the slide, poorly deployed additive is essentially just a replacement for traditional processes. So you'll take your existing parts that you currently designed for a subtractive process, and you're just simply trying to print them out. Again, that's not very optimized. It's a poor way to go about it. So a well-deployed additive process thinks about it as a new tool for improving manufacturing. It's an aid. So there's a regular overview required about the parts, feedback, and just essentially two-way communication between engineering and production. So as I mentioned, there really needs to be a two-way street for DFAM to work properly. So one common example we see is that management essentially provides a budget to engineering to get some new equipment and to start printing parts. That doesn't go well because essentially then there's no optimization, there's no feedback loop. So on the right, as you see the well-deployed additive, there's a two-way street going all the way from management to operations and all the way back. So that's the kind of workflow you want to develop in your organization to make sure DFAM is optimized well. So let's clarify what we mean by DFAM and where the benefits really lie. So the impact itself is highest for production parts and lowest for rapid prototypes. I hope that makes sense. If you're spending engineering time to optimize a rapid prototype, one which you may print one or two of, the cost time benefit may not be significant enough to justify the time spent to optimize it. On the flip side, if you're going to be printing batches of hundreds of parts, the time spent optimizing will pay off dividends when the material time savings are multiplied throughout the whole batch. Just to reiterate something I mentioned earlier, different additive manufacturing technologies require different types of DFAM optimization. To give some particular examples, the model you see on the left, if printed on FDM or SLA technology, could yield significant material and time savings if the bottom angle of the cup feature was just changed 5 or 10 degrees. For the model on the right, when printing in SLS or SLA technologies, providing escape holes in a hollow model reduces material usage drastically, while in FDM, it would yield no benefit at all. So again, just keep that in mind. So DFAM for results. So here is a list of essentially the primary benefits for design for additive manufacturing. On the left, you see 7 principles. We'll be going over those shortly, one by one. And on the right, you essentially see where those principles lie as far as reducing resources or enhancing the quality of the part. Okay? So principle number 1, thinking additively. So most of the engineers today think subtractively, right? Traditional manufacturing generally meant taking, a block of material and removing it from the block. So we really have to flip the whole idea on its head, because now the less material we use, the less cost and the more time we save. So it's really a different thought process as far as manufacturing goes. So it really needs to be explored. Here's a great example of a part here. We have an endo-arm tool for a robot. The original part was made out of aluminum. It was very heavy. It required quite a big lead time to manufacture. So the customer wanted to improve that. And here you can see the 4 iterations that they went through to come to their final design that you see on the right. And this yielded a number of benefits. So one significant aspect for robots is weight. The lighter the tool is for a robot, the cheaper the robot can be used. So reducing the weight of end-arm tools is very important. So as you can see in this particular case, they were able to take the weight and reduce it by 29 pounds, which over an assembly line of robots is a significant saving. So not only that, but the original tool had vacuum lines running to a vacuum gripper portion of it. And those vacuum lines would once in a while snag on some external parts and cause the whole operation to crash. So in this particular part, they were actually able to build the vacuum lines right into the interior of the part, something that with different methods would be significantly harder. So in this particular case, not only were they able to improve cost and time for the part itself, but they were able to improve their process as well. Here's another example, a very similar example, just a very big, heavy, bulky part. that took a very long lead time. It required many parts, so it had to be assembled, which again increases time and cost. So in this case, they were able to reduce it from 40 pounds to 4 pounds, increased lead time by 4 weeks, printed in one piece, so assembly time was significantly reduced, and there was also a significant reduction in cost as well. So another great example of DFAM being used properly. Another one, for example, by BMW. So on the left, you see the original tool that they used, that an assembly person would use to put a BMW badge on the trunk of a car. As you see, the original design is very, very blocky, made out of heavy bar stock, would take almost 3 weeks to manufacture, require lots of assembly, and just was a very cumbersome tool. So if you look at the tool on the right, the finished product almost looks like an F1 steering wheel, a much more ergonomic part, 28% of the original weight, so huge improvement in weight, significantly faster to produce. But one thing I'd like to highlight here is that not only are you able to improve time and cost of parts when you employ DFAM, but in this particular case, you can also improve, health aspects of your employees as well. So DFAM really goes well beyond just time and cost improvement. If you think of somebody who has to put, hundreds of those badges a day, using that ergonomic tool will probably lead to some healthcare savings for the company in the long term. So something to remember. So just to talk about principle number one, thinking additively, it just well-deployed DFAM requires not only new skill, but a new mindset. Again, it's really flipping from subtractive manufacturing to additive manufacturing. Principle number two, design for orientation. So as you can see, we have a tab feature, and we have it printed in 3 different orientations. And as you can see here, 1, 2, and 3. So orientation number 1 is printed on its side. That'll give it great strength and good accuracy. If you print in a variation like number 2, that would yield the fastest print. But it will not lead. It will lead to some critical features having stair stepping, so they won't look good. And number 3, standing up, will give it the best appearance, but it'll be the weakest part. So essentially, here it's just important to know that how you place the part on the printing bed will definitely lead to some differences when it comes to your final part. So always think about how you're orienting your parts. So another orientation. So in this particular case, you see 2 blocks. The block on the left is the part as it was, and the right part is the part that's been optimized. So again, depending on what technology used, in this particular example, we're using FDM technology. All those yellow orange surfaces that you see on the left model would require support material. So if those orange areas are not critical and they're allowed to be changed, if we change all the angles to self-supporting angles, like the model on the right, we could improve the print time and the cost quite significantly, as you see by the figures there. So this principle, design for orientation, requires maximum communication between engineering and operations. So operations, the people running the printers, will know what angles, for example, are self-supporting or not self-supporting, and they need to have communication with engineering to make sure that that is known and addressed. DFAM principle number 3, not the most common type, but one that is certainly used, is called contour design. So essentially, certain parts can be printed with just 1 or 2 extrusion lines. So when we're talking about extrusion lines, we're talking particularly about FDM technology. And with those extrusion lines, you can create some really strong, lightweight parts. So in this case, you see kind of like a wing feature. We see that a lot in printed drones and things like that. So just essentially a single thickness of the bead of the print allows you to create some parts that are really lightweight, really strong. So again, just to reiterate, maximum communication between engineering and operations for that to be realized. Principle number 4, one that's quite overlooked in my opinion. In this particular example, they were trying to print a windshield for the Slingshot. Some of you might have seen those around on the road, some pretty cool vehicles. And in this particular case, the windshield was just too big to print. So we've seen customers that say, hey, our part's too big for the printer. We're going to go with some other manufacturing method. So one of the simplest solutions in those cases is to simply segment the part. So just cut up the part in whatever sections that will fit in the printer and then just simply bond them together. A tip or trick with that is to use dovetail joints. There's different softwares that can help you with that. But those dovetail joints will make sure that, it's keyed properly and it will have the strongest kind of joint. Another different version of segmenting parts. So in this particular case, the whole part can fit in the printer, but it was realized that if a couple of the portions of the part were segmented away and printed separately, significant time and material savings could be had. So in this particular case, it was a masking fixture for car painting process, and you can see the handles on top of the masking part. So simply by removing the handles and printing them separately, they were able to increase time by 34% and savings by 26%. The one takeaway with that is you have to make sure that it doesn't become a traditional kind of design for assembly process. Sometimes we've seen clients who start to segment the parts kind of almost to an extreme where they're, lots of assembly time is then required again, and some of those benefits are negated. So just make sure you're aware that as you're doing that kind of segmentation, you don't go overboard. Principle number 5, adding hardware. So this is a great one. Essentially, there's many different kinds of hardwares that can be added. In that top example of that kind of tab-like part that we saw earlier, if you needed that part to be stronger than its plastic equivalent could be, you could simply model in a hollow cavity into the part using our Insight software for the FDM printers. And then you can literally pause the build right before that cavity is closed up, and you can insert a metal feature and then resume the print to have the printer essentially encapsulate that metal portion. So a really great way to create some strong parts. If you have any kind of hot or abrasive issues with parts, like the part on the bottom left, you can add kind of bushings to those particular areas that are having those contact issues. And you'll just make a functioning part from a part that just didn't work before. If you're trying to do kind of any kind of threading, any kind of threads, I personally recommend you don't print them. There are many better ways to go about this. So one recommended way is to go with heated inserts or helicoils. So that way you actually have metal threads in your 3D printed part, and it'll be great for long-term use. And then also, if you have any kind of magnets or anything like that you want to put in a part, there's always a quick way to put some locating features in there so that you can quickly snap it in and glue it in. Okay, so again, just kind of reiterate after every time, there's just close communication between design and operations to make sure that those all those kinds of design capabilities are properly communicated between back and forth. Number 6, minimizing complications. So this one's a little interesting because it kind of goes against the original idea of, the less material we have, the better. So if you're printing with FDM technology, a technology that requires support material, and you have a part like the part on the left side, that handle area of the part will have support material throughout it, all the way up to it. And support material adds significant time to the printing process because every layer the machine has to switch between model and support. So if we eliminate the support material, we can actually increase our print time significantly. So just like in this example, essentially a part was modeled in where the support would be because the part is used for thermoforming. That's not an issue. So in this particular case, by doing so, they were able to bring the print time down from 8 hours to 5.3. So rather significant. Minimizing complications, again. So this is an interesting one. We kind of see this happen. Clients try to optimize for material, and what they do is they'll take a model that they say they only need the exterior of, and they'll hollow it out completely, and then they'll put some supporting ribs inside just to give it some structure. And they'll usually model in some sort of thickness. So in this particular model, they modeled in an 1/8 inch thickness for all the surface. And they printed that and thought that that was great. But what they didn't realize is that if they were just to print it, the model solid, but using sparse infill, so with FDM technology, you don't have to print solid, right? You can adjust the interior fill of the plastic. So just by printing with a sparse setting and printing a solid model, it is actually over 10 hours faster to do it that way than with their intended optimization. So always be aware of that as well. Okay, so again, just reiterating again, this is a good one. when you're iterating parts, if you're trying to improve a part or you're having issues printing a part, and you're making some changes and you're printing it again, don't print the whole part if you don't have to. Iterate only the portions of the part that you're having trouble with. So again, if you're having some locking tabs on a part break off and that's the only portion that's having an issue with, don't keep reprinting that part over and over again. Just work on those tab features in the proper orientation. Principle number 7, surface treatment. So holes, for example. If you were to print a block just like this one with those horizontal holes going through it, hole number 1 would require support material. Okay, so if you're trying to increase print times and decrease material, one thing you can do is you can actually just undersize the hole and create a diamond shape instead, just as you see with number 2. So a diamond shape has self-supporting angles, so there's no support material that's going to be needed for that. And then that way you can just ream it after printing. And then number 3 is a great one if you need just clearances only. So if you're trying to run some wires through a part, something like that, you can just create a kind of teardrop shape to the top of the hole. And that will, again, create self-supporting angles and support material will be negated. Okay? So a great way to go about holes. Another thing with holes, so if you're printing with SDM technology, usually by default, the printers will print either 1 or 2 perimeters around the hole, and then it will kind of raster fill the surrounding areas. So if you plan on reaming the hole or tapping the hole, afterwards, it's great to add some extra contours to those holes so there's actually more material there, more solid material. So, for example, if you print a part that has very light, sparse interior, it's mostly air in there, if you only have 1 or 2 contours and you ream through those contours, you'll actually go right into the hollow air kind of gaps inside the part, and you'll you'll reduce the structural rigidity of the part significantly. So if you can use Insight software to modify those parameters and, again, create more contours around the part, so when you ream it, there's still plenty of solid plastic around that hole. Okay, so that requires detailed call-outs of engineering for operations. The guys running the printers just need to be aware that the reaming or tapping is going to be happening, so they can make the proper modifications in the files before they hit print. Okay, so just to summarize, again, those were the 7 principles we quickly went over. Think additively, design for rotation, contour design, segment parts, add hardware, minimize complications, and critical surface treatment. So as you can see, each different principle gives you different benefits in different fields. So based on whichever fields you're trying to improve, you can go ahead and look at that particular principle. And with that, that concludes our Design for Additive presentation.